if we're trying to estimate the relationship yi is equal to beta xi plus ui, we're implicitly making the constraint that the intercept of our fitted line passes through the origin. So our line will pass through the origin, and whilst the slope will be allowed to vary, the key thing is that the line that we draw must pass through the origin. So we could have any one of these lines being estimated, but in each case the line passes through the origin. Now, since we're placing that constraint, the estimator that we would need to use, the OLS estimator, would look like beta hat is equal to the sum between I is equal to 1 and n of yi times by xi over the sum of the x squared. So we're looking at the sum of the product of the observations of y and x divided by the sum of the x squared. Now we're going to make two key assumptions. The first assumption is that the data generating process is the relationship that we're estimating. So the data generating process is yi is equal to beta xi plus ui. So in other words, each observation of y is just equal to some constant beta times by the observation of x plus some random error term. And the second assumption relates to that error term, that the expected value of the ui conditional on any set of observations of x is equal to 0. And that means that the error term is effectively independent from all of the observations of x. Now we want to show that this OLS estimator provides an unbiased estimator for the true slope parameter. And remember, an estimator is unbiased if the expectation of that estimator is equal to the true population parameter being estimated. So in this case, it'll be unbiased if the expectation of beta hat is equal to beta. Now, when we're analyzing these estimators, the first place to start is usually to try and substitute in the data generating process for y. So that means that we can rewrite beta hat as being equal to the sum between I is equal to 1 and n. Substituting in our data generating process, yi is just equal to beta xi plus ui. Then that's multiplied by xi divided by the sum of the x squared. Now we can multiply out the brackets on the top here to give us that this is equal to the sum between I is equal to 1 and n of beta xi squared plus ui xi divided by the sum of the x squared. Now we've got a sum on this numerator which we can split up into two separate summations, and since we've got this common denominator, we can split this up into two fractions. So we can write this as being beta times by the sum of the x squareds over the sum of the x squareds plus the sum of the ui xi's over the sum of the x squared. Now we've got the sum of the x squareds over the sum of the x squareds here, so those are going to cancel, leaving us with just that we can write that beta hat is equal to beta plus the sum of the product of the observations of u with x divided by the sum of the x squareds. Now, in order to analyze whether or not this is unbiased or not, we need to take expectations of beta hat. So the expectation of beta hat is just going to be equal to the expectation of all of this. So this is going to be the expectation of beta plus the sum of the u x's over the sum of the x squared. Now this is the expectation of a sum, so we can split this up into two parts, the expectation of beta plus the expectation of the sum of ui xi over the sum of the x squared. But the expectation of beta is just going to be beta because beta is a constant. So this is going to be equal to beta plus the expectation of the sum of the ui xi's over the sum of the x squared. Now, in order to analyze this, we're going to need to use the law of iterated expectations, because calculating the expectation of this without knowing something about what's going on inside is more or less impossible. So we can write this as being equal to beta plus, we're going to apply the law of iterated expectations to this, and remember, the law of iterated expectations says that the expectation of y, for instance, is equal to the expectation over all possible values of x of the expectation of y conditional on the values of x. So this is equivalent to weighting all of the conditional expectations by the relevant probabilities of x. Now we're going to apply this slightly differently, and we're going to use the law of iterated expectations based on different sets of observations of x. So we're going to look at the expectation over all possible sets of observations of x of the conditional expectation of the sum from I is equal to 1 to n of ui xi over the sum of the x squared conditional on a particular set of x's. Now, in this summation, we've effectively got every observation of u is multiplied by xi divided by the sum of the x squareds. So we've got each observation of u multiplied by xi over the sum of the x squareds. And given that we're thinking only about a particular set of x's, we can treat those as effectively constant multipliers of the u, and we can take them outside of the conditional expectation. So this is going to be equal to beta plus the expectation over all possible sets of x. Inside the brackets, we're effectively thinking about one particular set of x's. So you've got the sum from I is equal to 1 to n. Given that we're treating the x's as fixed, we'll write them as a lowercase x. So the sum of the xi over the sum of the x squared times by the conditional expectation of u given a particular set of x's. But we already know from our assumptions that this conditional expectation is equal to 0. So we've got that this is equal to beta plus the expectation over all possible sets of x of 0 times by something, but this is going to all be equal to 0. So that's the expectation over all possible sets of x of 0, which is just 0. So provided our assumptions are correct, the expectation of beta hat is just equal to beta. And therefore, if our assumptions are correct, the OLS estimator is unbiased.